Okay, now for the final third of this lecture today. In this final lecture, I will discuss the regeneration of the original input signal, and there will also be a few topics that need to be discussed to wrap up this chapter. So first of all, let's try to address the question that I raised at the end of the second third of this lecture. It's a question, are we able to reconstruct the input signal? So just to remind you, we have this pipeline of components that we use for signal processing. We have the anti-aliasing, we have the sample and hold circuit, we have AD conversion, we have the processing or storage of information, say on the CD, and I presented one possible design of a DA converter, and now the question is, are we able to reconstruct something which is as close as possible to the original input signal? So let's look at this issue. First of all, it's obvious that the Nyquist criterion has to be met. If it's not met, we will certainly not be able to reconstruct the input signal, so therefore we have to assume that this is actually met. Then furthermore, we assume that we are sampling the original input signal at certain instances of time. These instances of time are denoted by TS, and between these instances there is a certain interval that corresponds to the sampling rate. So we assume that we have a constant sampling rate of 1 over PS, and this is then actually the inverse of the difference between any two of these sampling instances. So the question that I raise over here is the question, are we able to somehow interpolate between the different samples such that we are able to approximate the original input signal? And now I have to refer to the theory of sampling without actually being able to present you all the mathematical details there. Sampling theory tells us that yes, it's indeed feasible to approximate the original input signal, which is very nice for these people that like to listen to digital music, and we can do this in the following way. We can do this by summing up over all the different samples that we have for the different sampling instances there. And we have to consider a certain weighting factor that will interpolate between the values that we have for the sampling instances. Now, the interesting factor in this case is indeed this weighting factor. So let's look at the details of this weighting factor. So this weighting factor is called the Sinc function. The Sinc function involves the sine function and an additional expression there which results in a decrease of that sine function for larger values of the arguments. Now for this function we do have zeros for the case where the difference between these two instances in time correspond to the instances at which we are taking samples from the input signal. That means at where this expression is a multiple of the periods. So whenever this expression is a multiple of the periods, we have zeros. This is shown down here for the case where the period is 1 in this little graph, and there you see that for integer values there, this weighting factor actually has zeros. As a result of that, the weighting in this case works as follows. If as a time we are looking at a particular instance in time corresponding to one of the sampling instances, then only that particular value will actually contribute to the overall sum, but the contributions of all the other sampling instances will be zero, which is very nice because we know for this little graph, if we look at exactly these times, then the overall result for the sum will reflect just the value for that instance in time, and will have no influence whatsoever from the adjacent sampling instances. Now let's look at the different contributions there for the sample that I've used so far, for the sample that I already started to use for the very first lecture linked to this chapter. For this particular sampling instance, we have a contribution which is displayed in green over here. Obviously, for the adjacent integer times, the contribution there is 0. We see again over here it's 0, but then in between there is a certain contribution. And then for this sampling instance t equals 2, we have a contribution that is resulting in this red curve, and the red curve describes the impact of this instance of time to the adjacent times. And we have a similar observation here for the third sample. For the third sample, we have a contribution there in the neighborhood, except where the neighborhood is also one of the sampling instances. And the same applies for the other contributions over here. And now the question is, if we sum up over all these different functions, if we sum up over all the different colors, are we actually arriving at the input signal? And this slide shows the sum of all these different colors, and it is shown in red. For comparison, I'm also showing in blue the original input signal, and in green we see the signal at the output of digital to analog conversion. So there is some good news and there is some bad news. The good news is that the red curve at least is more similar to the blue curve than the green one. So we have achieved something, but we are not perfect. And in a minute or so, I will talk about the reasons why this approximation is not quite perfect. First of all, we will address the issue how we could possibly compute this weighting factor, because that's an issue which I left open so far, and there might be some concern. Because if we would try to compute that weighting factor using a digital signal processor, we would be completely lost. Because we are now back to the analog domain, and in the analog domain we don't have any DSP processor available. We can't just convert the signal back to the digital world, do the filtering, and then convert this back to the analog domain. That wouldn't really solve the problem. So this averaging, this interpolation, has to be done in the analog domain. And it's really interesting that this operation can only be done in the analog domain. It doesn't help if we are able to do this in the digital domain. So how can we do this in the analog domain? Well, we see it's a rather complex computation, and there may be some doubts whether there are some simple circuits that actually allow us to do this rather complicated computation. However, in this case, theory is really helping us. Because there is Fourier Theory, and Fourier Theory tells us that if we have an operation called folding in the time domain, this operation is equivalent to a multiplication in the frequency domain and vice versa. And now actually the operation that's supposed to be performed over here is indeed folding of our input samples with this weighting factor. So that means this folding can be replaced by a multiplication in the frequency domain. This, of course, then leads to the question, how can we convert this weighting factor to the frequency domain? What is the equivalent function in the frequency domain? Now, in this context, there is almost really good news. There's almost really good news because Fourier Theory will tell us that the corresponding Fourier transform of this weighting factor is a low-pass filter function. And this is a low-pass filter function. This is the low-pass filter function. For a low-pass filter function, we are not affecting the input signal in any way until we are reaching the cutoff frequency. And then beyond the cutoff frequency, the output is supposed to be 0. So that would be the purpose of a low-pass filter. And that means instead of having the rather complicated equation over here, all we have to do is we have to add a low-pass filter to the output of the DA converter. And this low-pass filter will remove all the high frequencies that are present in y of t. I mentioned that for a step function, we obviously would need a lot of contributions corresponding to high frequencies because we have to approximate these jumps there in the step function, and therefore this filter certainly is not redundant. It does have to remove all these high frequencies. Now the question is, how precisely are we actually reconstructing the input in that way? And there again, sampling theory is helping us because sampling theory tells us that if we really perform the computations in the way that is indicated in this equation, reconstruction would be precise. That means we would be exactly reconstructing the input signal, which would be very good news for people who would like to listen to music, because in that way we know that the music reconstructed from a digital CD is actually precisely reconstructed. However, I said that this news about the use of the filter is almost perfectly nice news. I was already indicating that there is a possible restriction there. There are actually a number of restrictions, and therefore there is a certain limitation. We can't really exactly reconstruct the original input signal. And we cannot do this for a total of at least 4 reasons. Maybe there are more than are shown on this slide. The first reason is that actual filters will not really compute this function, because I did already mention in the very first lecture corresponding to the 3rd chapter that there is no ideal low-pass filter. We can only have approximations, and therefore we have to accept that we will just use approximations, and finding good approximations is an art by itself. The second limitation is this one. The second limitation is resulting from the fact that this is a sum running over all the samples of the past and the future. Now obviously we don't know all the samples of the future, so therefore it's not really possible to take all of them into account. We can delay the signal by a few samples, and in this way we can have a kind of knowledge of some future samples, but it's not possible to know all the future samples, so therefore there is a second limitation with respect to this reconstruction. Third limitation is resulting from the fact that our anti-aliasing filter also is not a perfect filter. And therefore, as a result, there are already some higher frequencies implicitly present in the samples that we are processing. So therefore, there are limitations to exact reconstruction as well. And finally, obviously, quantization noise cannot be removed. I mean, this is something that we already see in this case. We see that there is a certain quantization. We have only used a total, a certain number of bits there for the conversion to the digital domain there, and therefore in cases where the analog signal is not actually matching one value that can be exactly represented, we have a difference there. In this case, actually the values are matching, so therefore there is no difference. In this case they are not matching, and in this case they are matching. So we see that because of the quantization noise, we will never be able to completely reconstruct the input signal. But as you know from listening to CDs, the result usually is pretty good, even though for some people not perfect. So this concludes the presentation of the conversion back to the analog domain. I will need to briefly look at the other components there in this hardware loop as well. There is a single slide that mentions displays as well. We know that display technology is a very interesting technology where there are lots of developments going on. We could have a separate course just on display technology, so therefore obviously it's hopeless to discuss all the different display technologies in this course. And also the output devices include electromechanical devices that can have an impact on the physical environment. Many of the electromechanical devices are requiring analog inputs, and that was one motivation why I actually looked at digital to analog converters. So the different motors or actuators that we can have there can be of a large number of different types. And again, it's impossible to discuss all the different actuators. If we just look at motors, I'd like to present this little motor here as an example. By the way, this is a motor from one of my toys that I used as a kid. It's from a Porsche-like car that I used to play with. So it's a pretty old motor. And this is a much smaller actuator. It's a small motor which is fabricated using microtechnology. With microtechnology, it's feasible to design extremely small motors that can be used, for example, for pumps that are built into the human body to supply a constant flow of medication if needed. And there are many other specialized actuators as well. Again, like I said, it's not possible to present all of them. Finally, for the sake of completeness, I do also have to mention in the context of embedded hardware, there is another area that I did not really discuss in detail, but in order to allow my dear colleagues to specialize a little further into that area and to have the appropriate hook for specializing into that area, I have this one slide that mentions the fact that in the context of hardware, we might also consider secure hardware. We know that in many cases security is needed for communication and for storage, and we know that therefore there may be the need for special equipment for cryptographic keys. We know that in this context it's necessary to resist side channel attacks like measurements of the supply current or electromagnetic radiation. There are special mechanisms for physical protection like shielding, sensors detecting tampering with the modules, and we do need to look at security from various aspects. We need to look at the physical security. We need to look at the logical security, where we have to make sure that the right cryptographic methods are used. As a special case, we might look at smart cars, which are a special case of secure hardware. The special situation there is that they have to run with extremely small amounts of energy. In general, it will not be possible to provide ultimate security under all circumstances, because there are also trade-offs between cost, convenience, and security that can be obtained, and therefore this balance needs to be considered for every application. There is no more information on this very important topic in this course. For those of you who are interested in secure hardware, I suggest to look at textbooks that are cited in the companion textbook. In this way, you can specialize in that direction if you want to. So this leads me to the summary for today. In general, in this chapter, we have looked at the different components that we find in the hardware in the loop. All these items listed in gray here have been discussed in earlier lectures. Today, I looked at communication. There, I did consider examples that meet the different requirements that we have for communication in the context of cyber physical and embedded systems. I did present the design of digital to analog converters. That was one special type of digital to analog converters. We did look at the key results from sampling theory regarding the feasibility of the reconstruction of the original input sample. We very briefly looked at actuators and secure hardware, knowing that these two areas cannot really be covered at any level of depth in this course that is intended to provide a broad overview over this area. Thank you very much.